Transformations of functions. So f of x plus k, it says shifts the function up and down. If k is positive, the function will shift vertically up. If k is negative, the function will shift vertically down. Okay, so it's all because of this. We have f of x and then this whole plus k part. So when you have a plus, any sort of number, that k just represents a number, outside of the f of x portion, you just take fx and you either add a number or subtract a number that's going to shift it up or down. So let me show you what I mean by that. So with this table here, it says the graph of f of x is shown, graph f of x plus 3, and complete the corresponding table. So how this would work, if f of x is 8, then f of x plus 3 would just be 11. 8 plus 3 is 11. 3 plus 3 is 6. 0 plus 3 is 3. Negative 1 plus 3 is 2. 0 plus 3 is 3. 3 plus 3 is 6. 8 plus 3 is 11. So that would be what the table would look like, right? Because if you have your f of x column, and f of x plus 3 would just be adding 3 to it. So say we were to graph this, and this is really going to show us what I was just mentioning. This is our x values and this is our y values. If we were going to graph f of x plus 3 per se, we'd have a point at negative 1, 11, which would be here. We'd have a point at 0, 6, which would be here. A point at 1, 3. A point at 2, 2. A point at 3, 3. A point at 4, 6, and a point at 5, 11. So the takeaway here is that if we have a function f of x and we do f of x plus 3, that graph is going to shift up 3. Let me illustrate that and kind of what happens. So if I look at, say, this vertex, I guess, of this is shifted up 3. Right, that's 3 units if you count the lengths. Even here, this has gone up 3. Here, it's gone up 3. All of these points, you don't need to write what I'm writing in green, but all these points here are being shifted up 3. Okay, so when you have f of x plus k, if k is per se a positive 3, it's going to shift up 3. So like on 2. I'm going to do 2 as well. So we have f of x, which is this linear line here. We're going to graph f of x minus 5. So if we do f of x minus 5, so let's say we have f of x here. This is the points on this regular f of x graph. If we subtract 5, this would be negative 7. This would be negative 5. This would be negative 3. This would be negative 1. This would be 1. This would be 3. This would be 5. I know I went fast. And so if I were to graph f of x minus 5, these are my x values, and this would be somewhat like my y values. If I were to graph this, what we should see is that this is just that linear line, except down 5, because it's f of x minus 5. Okay, so let me plot these points anyways. Negative 3, negative 7 be here. Negative 2, negative 5 is here. Negative 1, negative 3, 0, negative 1, 1, 1, 2, 3, and 3, 5. So just to reiterate, basically what we're seeing here is that, look at that point, for example, it has been shifted down 5. Even this point shifted down 5. So every single, point on the graph, it's just a vertical shift down 5, and that's all because of the f of x minus 5. So when we have a number, let me just recap here. So just to reiterate these notes, if we have an f of x and we do a plus or a minus to that f of x, if it's doing plus that number, it's going to shift up. And if you do a subtraction that number, it's going to shift down. But there's also going to be shifts not just vertically up and down. We're also going to have shifts horizontally left and right. Now here's the trick though. If k is positive, the function will shift left, which is weird. it's going to shift left. So when you say plus, you think, oh, plus, I'm going to go right. So, and what difference on this one is that the plus k is in the parentheses on this one. Okay, so if you have f of x and then plus k close parentheses, this is going to be the shift left and right. But the trick is, if k is positive, you're going to shift left, and if k is negative, you're actually going to shift right. You're actually going to shift right. So it's kind of like when we dealt with absolute value and vertex form. It's the opposite of what's in the parentheses. Again, it's the kind of like the opposite of what's in the parentheses. So let me show you a couple examples. The graph of f of x is shown below in each coordinate plane. Graph the shifts of f of x on the same coordinate plane. Okay, so this one here, f of x plus 2, is actually going to go left 2. That one's going to go left 2. And let me just kind of write this one. This one's going to go right 4. So when it's in that parentheses, that's going to give us a horizontal shift. You're actually acting upon that independent variable x, and you're going to go left 2. And we're not going to get into the table representations of this, but we're going to go left 2 on this one and then right 2 on the other one. So here, if I were to kind of move all these, but maybe I'll move the vertex first here. So I'm going to go left 2 there. So I basically am just kind of look at the slope of this. It's just going down over 1. I just have shifted it left 2. Meanwhile, this one says right 4. So if I were to move this to the right 4, the vertex would be there. And it's still it's going to maintain this shape where the slope's kind of going down 1 over 1. There you go. And it's been shifted right 4. So here's some practice for number 4. It says the graph f of x is shown below on each coordinate plane. Graph the vertical or horizontal shifts on the same coordinate plane. So you're going to determine, okay, is it going to shift up and down? Is it going to shift up? Is it going to shift down? Is it going to shift left? Is it going to shift right? So, use these notes up here in these examples. You don't have to do the tables with these. Just shift the function. Okay, so those are the sorts of transformations where you have a vertical shift or a horizontal shift. But now let's look at what we call stretches and compressions. Okay, so here's some notes here. So in this case, we have a number that's being multiplied to f of x, k times f of x. So the notes here say, if k is greater than 1, the function will vertically stretch. If k is between 0 and 1, the function will vertically compress. If k is less than 0, meaning it's negative, it's going to reflect over the x-axis and have the same rules as above. Okay, so let's explore this a little bit with number 5. It says the graph of f of x is shown. Graph 3 times f of x and complete the corresponding table. So 3 times f of x. So we have f of x and 3 times f of x. 3 times 3 is 9. 2 times 3 is 6. 1 times 3 is 3. 0 times 3 is 0. 1 times 3 is 3. 2 times 3 is 6. 3 times 3 is 9. So if I were to graph this, remember these are my x values. These are my 3 f of x values. I would have a point at negative 6, 9, which would be way up here. I'd have a point at negative 4, 6. I would have a point at negative 2, 3. I would have a point at 0, 0. I would have a point at 2, 3. I would have a point at 4, 6. And a point at 6, 9. So the takeaway here is that since we multiplied it by 3, which is a number, if you look up here, greater than 1, right? We're talking about greater than 1, then it's going to be a vertical stretch, right? It's going to be a vertical stretch. So like this was our original. Now it's stretch. It's like, if you're like this and you're stretching up, this is called a vertical stretch. Okay, so this is vertical stretch when we're multiplying f of x by a number greater than 1. So now let's look at this example. Now we're doing 0.5 times f of x. 0.5 times f of x. So 0.5 is less than 1, right? It's 1/2. 0.5 is less than 1. So we should be seeing a compression based off those notes up there. So this is our f of x. We're doing half of f of x, 0.5 of f of x. So 20, half of 20 is 10. Half of 10 is 5. Half of 4 is 2. Half of 2 is 1. Half of 4 is 2. Half of 10 is 5. Half of 20 is 10. So now let's just graph this to see if we see that vertical compression. So negative 5, 10 is here. Negative 3, 5, about there. Negative 1, 2, 1, 1, 3, 2, 5, 5, and then 7, 10. So if I were to draw this, it's still a parabola, right? It's still this nice curve. But the best way to kind of describe it, or the way I see it, is it looks like it's been flattened, right? You had your normal U-shaped curve, right? And now it's been flattened. We call this a vertical compression. You're compressing it down, right? Compression. So vertically, because vertical is up and down, right? We're compressing it. So we call this a vertical compression. And that's all because, if we look at our notes up here, that number being multiplied to f of x is between 0 and 1. That's going to show us a compression, right? If you multiply a number by like a decimal less than 1, it's gonna get smaller, right? So that's why we see the y values or this kind of the dependent variable. It gets smaller, hence the compression. Okay. Now let me show you sort of the last example here, and that's when we slap a negative in front of it. Okay. So now we're doing negative f of x. So if f of x is this, and we want negative f of x, it would be negative 7. It would be negative 5. It would be negative 3, negative 1. Negative 1 would be positive 1. So now it's positive. Negative 3 would be positive 3. This would be positive 1. This would be negative 1, negative 3, negative 5, negative 7. So we just did the opposite of all the f of x because it's negative f of x. So now I'm going to graph this and let's see how this looks. So negative 7 would be down here. Negative 6, negative 5 there. Negative 5, negative 3 here. Negative 4, negative 1 here. Negative 3, positive 1 here. Negative 2, 3 here. Negative 1, 1 here. 0, negative 1, 1, negative 3, 2, negative 5, and 3, negative 7. So here we go. So what this looks like, it looks like a flip. Originally, the V was the absolute value graph was like a V, like this, and a right side up V. And now it's been flipped down. Now it's an upside down V. Now, more specifically, it's not just that it just flips. And this is where a lot of students don't see this. When you put a negative in front of it, it doesn't just flip. It flips over the x-axis. Okay, I'm going to draw a little dotted line here. It actually flips over the x-axis. And I keep using the word flip, but the mathematical term is what we really call it. We call this a reflection. It reflects over the x-axis. And I know you've done reflections back in pre-algebra. So you should have some familiarity with reflection. So for instance, if this vertex is 3 points from the x-axis, you would reflect it 3 points up here. as well. So this is reflects over the x-axis, okay? So when you have a negative, whoops, it's going to reflect over the x-axis. And I think that's, yeah, in the notes here. So if k is less than 0, the function will reflect over the x-axis. So that's what it would look like. So I'll let you do these matching. You try these matching. And let me show just a few of these examples. Okay. It says the graphs for f of x are shown. Describe and graph the transformation of f of x on the same coordinate plane. So I'm going to do B here. So since this is outside of the parentheses, this means we're going to have either a shift up or a shift down. Since it's -2, this is going to be a shift down 2. So I'm going to basically take all the points on this graph, those points, right? All these points, and just shift it down 2. Here, here, there. Entire graph is just being shifted down 2. It still maintains the same slope and kind of shape, if you will. It's just now been translated, would be the technical term, down 2. Okay. So you should be able to do A based off of that. C, and even D. Now we have a number inside the parentheses. So this is going to determine whether or not we shift left or if we shift right. That's what the number in the parentheses is going to help us determine. Now, remember, like I said, it's weird. It's going to be the opposite of what you think. So since it says +3, you might think, oh, it shifts right 3. No, no, no. This is going to be left 3. So I'm going to take all the points on this line and go left 3. So let me just kind of pick some points, I guess. So I'm going to go left 3. So that's going to be here, here, here. And then it's going to look like this. I'll do another one. Okay. Shifted left 3. Let me do E. So E says 2 times f of x. So we know since we're multiplying by 2 on this, it's going to be a vertical stretch. If it was less than 1, again, like say like a 0.5 or a 0.4 or I don't know, anything between 0 and 1, less than 1 there, it would be a compression. But this is 2 times f of x. This is going to be a stretch. So kind of the way I like to think of it is this point's going to stay 0, 0, because if I multiply the y value 0 times 2, it's still going to be 0. This point, though, 2, 1, if I multiply, again, we're just multiplying f of x times 2, the y value by 2. This point at 2 is no longer going to be at 1. It's going to be at 2. Because 1 times 2 is 2. Let me show you another example there. That might not have been the best one. So this is at this point is at this point here is at 4, 2. And since we're multiplying by 2, now it's going to be at 4, 4. Okay. So this is just we're just acting upon the dependent variable, which is y. We're just doubling the y value. Like for instance, this point's at 6, 3. Well, 3 times 2 is 6, so it's going to be at 6, 6. This point's at -2, 1. So 1 times 2 is going to be at -2, 2. This point is 2 up, right? It's 2 up. So now it's going to go 4 up. This point here is 3 up currently. So if we double it, multiply it by 2, it's going to be 6 up. So that's what it's going to look like. Okay, so I'll let you do F. That should be your reflection. Okay, number 10 says the graphs of f of x, g of x, and h of x are shown. Write the equations for g of x and h of x as a transformation of f of x. Okay, so f of x is the main function here. This is the original function. And I want to write rules for g of x and h of x based off of f of x. So this is my, maybe I'll just like highlight it really quick. Like this is the original one. Okay, the f of x. That's my original one that I'm going to be looking at. So if I'm trying to write this as g of x per se as a transformation of f of x, if you look at g of x, it just looks like it's been shifted up, right? It looks like it's been shifted up comparatively to f of x. It looks like g of x is a shift up of f of x. Well, how much is it shifted up? You just count. It looks like to me 1, 2, 3. It's been shifted up 3. So g of x is f of x plus 3. Now, h also looks like a shift or a translation over, and it looks like it's gone to the right, right? You take f of x and you go to the right. So h of x is how far to the right? It looks like 1, 2, 3, 4, 5. It looks like it's gone 5 to the right. So remember how we expressed that with the horizontal shift. We're going to go f of x, and then since it went right 5, remember it's weird. We got to do the opposite in the parentheses. So it's going to be minus 5. That indicates a shift right 5. I'll let you try 11. Let me just do A on 12. So now we have tables. Write the equations for g of x and h of x as a transformation of f of x. So g of x, so let me highlight. So f of x is this, right? And if I look at g of x, what pattern do you see? Doesn't it look like we're just subtracting 4? It looks like just a shift down of 4. 9 minus 4 is 5. 4 minus 4 is 0. 1 minus 4 is negative 3. So g of x is just a shift down of 4, correct? So I'm going to write g of x equals f of x subtract 4. Okay, I'll let you try the rest.